So what we're going to do is looking at application of derivatives this time, thinking about how we could find the stationary points and extrema. Alright, so stationary point is when you have the point of inflection where the dy dx is 0, or minimum or maximum where dy dx is 0. Alright? So what you need to do is be able to recognize that calculus can be used to locate critical points on a function, including stationary points, maximums and minimums. Now, the sign test is important at this stage. For this year, we want and expect you to do a sign test. You are not expected to do the second derivative to find the stationary point. Alright? We want to know that you can do a sign test so that you could understand what the stationary point is. So no, not using the second derivative. I know some of you have learned it, but I would just recommend that when you do the assessment, make sure that you know how to do a sign test. Alright? So now looking at the first graph, we know that for a function fx, the stationary point is when the first derivative is 0. Alright? So we look at things like maximum turning point, local maximum, which is something like this, point A. Alright? Minimum turning point, point B, and horizontal point of inflection, point C. Now, what I want you to think about is the concavity, or that's lack of concavity, which is C. There's no concavity, but yeah, it is a concavity, not lack of it. It's just that the change is very subtle. Alright? So that is a horizontal point of inflection. What I want you to think about is using the first derivative, looking at the instantaneous gradient. Alright? What happens when the gradient approaches A and then it leaves A? When the gradient approaches B and then it goes away from B, approaching C, and when it goes away from C. Alright? Now, looking at this, what is a gradient? Is it positive or negative?
Positive.
Positive. So let's go out from here, positive. And then leaving that is negative. Correct? Yeah? Notice that. Let's concave down, you go positive and then negative. What about here? You go from negative to positive, correct? Yeah? So this is local minimum. You go from negative to positive, and the concavity is concave up. Here, you go from positive to positive. Positive to positive. Sort of like, yeah, that's a, sort of, yeah, it is, that's a, it's concave, sort of concave up, and then concave down, that way. It's really hard to tell. But you know that in that case, if you got a sign of positive and positive, before C and after C, it's actually point of inflection, horizontal point of inflection. So what I've done is show you the 3 stationary points. Of course, it could have something like this as well. That's another stationary point. This could be a C as well, correct? So this time, in that case, it goes from negative to negative. That's your slope. So I want you to bear that in mind. Think how we are going to use this positive, negative, the sign test, to determine whether the stationary point is maximum, minimum, or horizontal point of inflection. Alright? This is what I want you to think about. How to use the sign test. How to use the instantaneous rate of change. Everyone happy with that?
Yep.
Alright, let's move on. Now, first example. Use calculus technique to find the coordinate of the stationary point of the function x squared minus 4x plus 7. I plotted a graph there. You know that it is a minimum. Correct? So what we need to do is first go with dy dx. Find the first derivative. We know this is 2x minus 4. Right?
Yeah.
So at stationary point, dy dx equals to 0. Therefore 2x minus 4 equals to 0, and x therefore equals to 2. So substituting x in, y therefore equals to 2 squared minus 4 times 2 plus 7, 4 minus 8 plus 7, which is 3. So the stationary point is 2, 3. Now, without the graph, if the graph is not there, you know that it has to be a minimum because there's a positive x squared. The coefficient for the x squared is positive. So it therefore you know is a positive. But when you come to situation like you've got to the power of 4, to the power of 5, to the power of 6, and so on and so forth, sometimes it's hard to tell. Because something to the power of 4, it may look like this, which is a W shape. Which one is positive, which one is negative? You don't know. To the power of 5 a quintix, you may have something like this. Alright? So it's pretty hard to tell when you come to that sort of situation. Therefore, you need to do a sign test. Alright? So let's think about how to do it. Now here, without a graphical representation of the function or prior knowledge of the function itself, we currently do not have a way to determine the nature of the stationary point. You can plot the graph, then you can determine the nature of the stationary point. But really, we can't do it without the knowledge of the function. So let's have a look, same example. Oh no, actually, let's talk about the first derivative test first. We can use the first derivative test to find the nature of the stationary points. Now, given that a function fx has a stationary point at a, fa, where f, the first derivative of a is 0, the instantaneous rate of change is 0, then we can test the gradient function for values of x on either side of x equals to a and examine the nature of the gradient, plus or minus. Alright? Think about it. We need to think about the plus or minus of the gradient. Alright, let's have a look at this. I would like all you to concentrate on this one now. Alright, if you're going on to do all the other, please leave it aside. Concentrate on this slide. Thank you. It's quite important for you to think about what we should do with this. Now, with minimum turning point, what does the shape look like? Sort of like a U shape. It doesn't matter whether it's a quadratic or a quintic or whatever it is, or cubic. You could have something like this. You could have this. You could have this. You could have this, and these are all the minimum, correct? Yeah. Yeah? So, what does it look like? The shape of it is something like a U, correct? It doesn't matter what sort of graph you have, it looks like this. Alright? So, if you look at doing a sign test, if that is A, alright, this point is x equals to a. The gradient, when it is less than a, is actually negative. So what you do is draw something like this. So you indicate to yourself is that at the point A, the gradient is 0. Put a horizontal line down, and then when x is greater than a, that is positive. Let me do it properly. Positive. So therefore it's something like this. So here you can see that that point from negative 0 to positive is actually a U shape. So therefore it's a minimum, local minimum. Now maximum turning point. Same thing on my on the screen. Not on the screen, on the whiteboard. This point is maximum, local maximum, maximum. That's none. Local maximum, local maximum. What does it look like? Inverted U, correct? It's sort of like an N shape. So all that looks like something like this. So it doesn't matter what sort of graph you have, you got to think about at this point here when x equals to a. Alright, when x equals to a, the gradient is 0. So horizontal line. Now, if you go from here onwards less than a, the gradient will be, what would that be? Positive. So that way, and then therefore the next one will be negative. Correct? That's coming down. Yeah? So if that's negative, you've got a shape. That is telling you what the shape is. It goes up and then down. So the sign has, all the teachers have certain way of doing things. This is the way I like to do it. Look at smaller, the actual value itself, and something that's greater. Alright? Some teacher will pick a particular value, but the value is less than a or greater than a. It doesn't really matter. What I want you to do is think about generally when it's less than a, what happened. Now, let's talk about the horizontal point of inflection. So, it could, I could have something like this. Or I could have something like this. And then, alright, here I've got a horizontal point of inflection. I've got a horizontal point of inflection. Alright, this is a minimum. Correct? This is the mean. So it really, the shape, it could be any sort of function. You could think about that in that case is the first one, variation 1, it looks something like this. Alright? Here, it looks something like this. Yeah? Happy with that? So you do know that at that point, so we know that everything here, when x equals to a, the instantaneous gradient, rate of change on the gradient at a is 0. Now, horizontal point of inflection, this one. Variation 1, you go positive, correct? Yeah? And then positive. So that's a sign test for you. You go that way, horizontal, and then positive. And then the next bit, it looks like this. Alright? That way. So you go from negative to negative. So think about your graph. The minimum turning point, the maximum turning point is not necessarily restricted to your quadratic. It could be cubic, it could be quadratic, it could be quintic. But this is just a local shape. The local shape, the local shape, and the local shape. Alright? I'll give you a couple of minutes to write this one down. Fill in your table. Keep that table. These are what I would expect all of you to do in the test or in the assessment. Be able to sort out the point where the gradient is 0, less than x, x less than certain, x is less than a, x is greater than a. What is the gradient? It may not be 1 point in a function. It may be 2 points, it may be 3 points. You may be asked to find 3 points, which is what I'm going to show you in an example later. And then from there, you'll be asked to sketch the graph. Alright? Start from the basic, and next year you will learn the second derivative, where you will actually find the same thing, whether it's a local maximum or local minimum. Happy for me to move on? Yeah? Okay, let's go on. Alright, now, here. This is the first example. Show using calculus technique that the stationary point at 2, 3 on that curve is a local minimum, which is a minimum turning point. So find dy dx is therefore 2x minus 4, correct? So dy dx at x equals to 2 equals to 2 times 2 minus 4 equals to 0. Alright, watch please. Follow me in terms of how you do your table. So you've got a table here, x dy dx. Give it 3 columns. You've got x equals to 2. X is less than 2, x is greater than 2. So you know, let's not worry about this graph first. When x is 2, you know that dy dx is 0, so that is a stationary point. Less than 2, use any value. Say for example, x is 0. What will happen? It will be negative 4, so it's negative. So negative is that way. Alright? It doesn't matter whatever number you use, as long as you use a number. In this case, I use 0. Alright? Some teacher may ask the student to write a particular number in there. But it really doesn't matter. Whatever it is, I prefer this sort of convention. Less than or greater than. So you know exactly what you're doing. So greater than 2, if I use 10, 20 minus 4 is positive. You don't even have to work out the exact value. As long as you can see it's positive or negative, that's all. Alright? Once you know it's positive or negative, so therefore 2, 3 is a local minimum. Alright? So this is what you need to construct in an assessment situation using calculus technique. Alright, now let's start thinking about this. Determine the coordinates and the natures of all stationary points on the function. Alright? Before I start, can you all actually work on the first derivative? Using the first derivative, find the points. Alright? Find the stationary points. I'm going to freeze that for a while. Alright? Now, so far, this is what I got. Do you all agree with me? Yeah? Alright, the next step. You want the coordinates. So if you want the coordinates, substitute all the numbers in. So therefore, f0 equals to 1. So one of the coordinate is 0, 1. f2 equals to 3 times 2 to the power 4 minus 4, 2 to the power 3 minus 12, 2 to the power of 2 plus 1 equals to minus 31. 2 minus 31. And then f of minus 1 equals to 3 times minus 1 to the power of 4 minus 4 minus 1 to the power of 3 minus 12 minus 1 square plus 1. That is minus 1 minus 4. Oh, sorry, minus 4. Minus 4. So the three stationary points are minus 1, minus 4. Alright. before I go on, let's think about how we're going to set up the table. Alright, you know that there are 3 points there. When x equals to 0, x equals to 2, and x equals to minus 1, there are 3 stationary points. Yeah? So you have to make sure that you have got enough space to do things that you need, which is something like this. Alright, let's go from x dy dx, or actually I should use the same notation, f dash x. Alright, so the smallest x will be minus 1, so therefore it's less than minus 1. And minus 1. Now the next one is between minus 1 and 0. So minus 1, x, 0. Alright, then the next one is 0. And it's between 0 and 2. And the next one is x is greater than 0. Actually, I just need to write down greater than 0. Yeah? You can see that there's sort of like, that's 1, 2, 3, 4, 5, 6. 6 distinct regions for the graph. The 3 of them would be stationary point. This one, I don't know yet. That should be greater than 2, not not greater than 0. Alright, this is how I want you to actually do something like this. Now, you can straight away, in your table, fill that in. Hang on, I missed something. I missed the 2, and then greater than 2. 2, and then greater than 2. Alright, so this is 0. Yep. Happy with that? No? So once you've got this table, what you need to find is whether this is positive or negative, positive or negative, positive or negative, positive or negative. Right? And then you can actually plot the graph. So if it is less than minus 1, look at this. You are looking at using this. Alright? Alright? So how do you use it? So if we go for something like minus 10, you know that that's negative because minus 10 minus 1000, right? Yeah, that will be minus 10 minus 10, that is plus 100, but it's minus 12, so it's negative. This 2 number is greater than that number, so therefore it is negative. Alright? Yeah? So do that, you don't even have to, you don't even have to actually work out the number itself. Negative, that looks like this. Right? Now, between minus 1 and 0, let's say 0.5. 0.5, that would be minus 0.5, that will be plus 12. Correct? And then that would be 0.5 squared is 0.25, that will be less than 12. Right? That will be less than 12 again. So therefore it's positive. Got it? Yeah? You don't actually have to find a number. Just think about how you would do it, how you would find the sign, whether it's positive or negative, positive or negative. So now, between that, let's say we use 1. 12 minus 12, that's 0. 0 minus, that's negative. Which is that way.
So why'd you do that?
Sorry, that's that way. Yeah? So it's negative. See how I do it? I don't actually work out the number. I just look at the sign and look at what number is the largest and take away the smallest number. And then finally greater than 2. Greater than 2, let's use 10. That will be positive, huge number. That will be a lot smaller, so if I use 10. Yeah? So therefore you know that it's positive. Alright? So looking at the graph here, you can see that it's like that, and then up, and then down, and up. Got it? Yeah?
Yeah.
That is how it looks like. So therefore, the first point here, that would be -1, -4. What would that be? That is minimum. That would be 0, 0, 1 maximum. And therefore the other one is 2 minus 31. That is minimum. I should use local, sorry. Local. And the shape is something like this. Sort of like a W shape. So therefore, let's go to the next bit. How are we going to show the stationary point, y-intercept, and behavior of the function? Alright, let's think about what we could do. What I'm going to do is, I'm actually going to copy this one down if I could. Alright, so copying that down, I know that if it is x, oops, sorry. So it makes more sense. I mean, normally you will have it on the same page, but because I'm on the second page, so I'm going to write it down, copy that again. X less than -1, -1, -1, x 0, 0, 0, x 2, 2, and greater than 2. Alright, so you know negative, which is that way, that is positive, that is negative, and that's positive. Alright, so you know the general shape. What is the y-intercept? What is the y-intercept? 0, 1. Thank you. Always use your coordinate when you state your y-intercept. Alright? 0, 1. We don't know the x-intercept. It doesn't really matter. We have 3 points. -1, -4. 0, -1. And 2, -31. So you can see that, sorry, that's 0, 1, not 0, -1, that's 0, 1. So you can see that the y-intercept is actually one of the stationary point. 0, 1. The next one is -1, -4. Let's call this -1, -4. And then 2, -31. 2, -31. So you know the shape. This is minimum, maximum, minimum, and that's it. That's your general shape, sketching it. So using your calculus technique, you know what the shape looks like. You know you can estimate the point. So you can actually draw with the 3 points, draw your shape out. Sketch the function. Can you all see how I've done it? How I've used your calculus technique, finding the gradient before and after the stationary point to see which one is negative, which one is positive, and hence sketch the graph. Alright, if you look at something like a quadratic, what is the degree of the first derivative? What would that be? 3? Yeah, 3. So what is the maximum number of stationary points you would have? 3. Because you can solve x 3 times. Right? So sometimes you don't, sometimes it's only, it depends on what the coefficient is, you may only have 1 for quadratic. Alright, it may be a U shape. it may be a W shape. So you've got to think about, in that case, quartic, you will have maximum of 3 turning points. A quintic generally, quintic of 5 to the power of 5, the degree of 5, the first derivative is 4, so therefore your the number of stationary point, maximum number of stationary point is 4. Alright? And so on and so forth. Alright, now, sometimes you need to find the extrema over a restricted domain. You may not necessarily need to find every single thing. For example, this question. How do we actually find the local maxima? How do we find the extrema or a point of inflection if we are restricting it to -1 and 1? Alright, from the graph, you know that that's only 1 point. Correct? But in fact, without the graph, you wouldn't have a clue what that is. You really don't know. The graph I plotted for you, you know that we've got 1. So let's have a look at the last example. You are now asked to use calculus technique to determine the coordinates of the maximum and minimum value of that. So you know, therefore, you can do the first derivative, which is 12x squared minus 4x cubed. Correct? Can you solve that, please? Can you find first what the points are? The point between 1 and 4. All right. Now, you are not asked to plot or anything, but you have to know that we are looking at the domain of between 1 and 4. So we can totally ignore x equals to 0. Correct? All we want is when x equals to 3. So you can see that this is a quartic, and you've got 2 stationary points. We are only interested in 1, which is when x is equal to 3. So, again, what we need to do is x, fx. We need to know that when x is less than 3, 3 greater than 3. All right. Now, when you're looking at this, obviously, you can no longer use x equals to 0, can you? Because x equals to 0 is a stationary point. Hang on. You can't use x equals to 0 because it's a stationary point from here, although it's less than 3. You cannot use anything less than 0 as well. Correct?
Yes.
Because if you use anything less than 0, you still have that stationary point of O. So let's use between 3 and let's say you use 1. If it is 1, 12 minus 4, that's positive. Which is that way. So this is, and greater than 3. So greater than 3, let's use 10. That will be negative number. This is, if it is 10, this is minus 4,000. This is 100, 1200, so it's negative. That way. So 329 is a local maximum. All right, the shape should look something like this.
Yep, maximum.
Local maximum. So you must be able to use your idea, your knowledge of first derivative to actually find your stationary point, and then use your calculus technique, looking at the gradient to find your whether it's local maximum or minimum. All right, of course you need to find a coordinate as well. Now, the next bit is a summary. It's up to you how you want to do your summary. All right, it's up to you how you want to do your summary. So finding stationary point, for example, you could just write down or dy dx equals to 0. All right? So give yourself what is the nature of stationary point. What do you want to look for? All right? And show the maxima and minima of functions. All right? How do you show that? Do a summary, and then I'll show you my summary. So this is the time for you to do your summary. You can refer back to the table that I've shown you. All right, my quick summary of the whole lesson. It's up to you. It's your summary, so make sure that you know what you want and perhaps use this and stick it in your book, all right? I'm going to stop here now, and there should be plenty of exercises for you to do.